Hi everyone. Today we're going to talk about the overview of section 11.5, which is general Frobenius theory. What we mean by that is we're going to be looking at cases where the index equation that we looked at in 11.4 has roots that are real and repeat, or has roots that are distinct and differ by an integer, or has roots that are complex. If you're interested in the technical details behind the proofs, then you can look at the accompanying videos that I made that sort of walk through the theory of what's going on. The point of this video is to give you sort of a high-level view of how Frobenius theory works and how we decide what the form of the solutions we're looking at is, and if we know what the form of the solutions is, how we actually determine what the series solutions actually are in terms of their coefficients. So to begin with, let's remind ourselves about what the situation is in the case that we looked at in 11.4. So in 11.4, we cooked up a general sort of approach to differential equations that have singularities in the case of regular singular points. And the ideas that we need here are the general form of the equation, which looks like x squared y double prime plus xp of x y prime plus q of x y is equal to 0, with the additional assumption that p and q are analytic. And remember what that means is that p and q have power series representations. For some radius of convergence, which is positive. If we have this setup, then we can use the Cauchy-Euler index equation to figure out what the solutions look like in at least one case. So the indicial equation is the quadratic equation r times r minus 1 plus p naught r plus q naught is equal to 0, where p naught and q naught are the first terms of the power series, but what that means is they're actually the values of p of 0 and q of 0. In the previous section, what we assumed was that the values r1 and r2 that came out of the quadratic were both distinct and they didn't differ by an integer. So the case that we've already covered is that the solutions to this are r1 and r2, and r1 and r2 are distinct, and r1 is not equal to r2 plus some positive integer n. As long as we have that assumption, which is quite a bit of assumptions actually, given the way that the roots to a quadratic polynomial can turn up, then we can assert that this function has two linearly independent Frobenius solutions. And what we mean by that is if I have all of this structure, then I can assume that y1 of x is x to the r1 times the sum from n equals 0 to infinity of an x to the n, and that y2 of x is x to the r2 times the sum from n equals 0 to infinity of bn x to the n. So if I make all those assumptions, then I know that I've got two series solutions which are called Frobenius series. So what happens in all of the other cases? After all, there's a lot of different ways that we could have a quadratic equation and solve for the roots. The roots have lots of different ways they could be related to each other. So what I mean is, so far we can cover this case. If we wrote down the equation r times r minus 1 plus p naught r plus q naught is equal to 0, the case that we've analyzed is r1 and r2 are real and distinct, and r1 is not equal to r2 plus n. We're always assuming that r1 is the larger of the two solutions in the case where they're real. But there's other cases that we haven't considered yet. It could be the case that r1 and r2 are real and distinct, and r1 is equal to r2 plus n. What about that case? Or r1 and r2 could be equal to each other. Now that can only happen if they're real. I can't use the same series for two different linearly independent solutions, so something has to happen. What about that? And finally, it could be the case that R1 and R2 are complex. Quadratic equations can have complex roots, and quadratic equations with complex roots that have real coefficients always have complex roots that occur in conjugate pairs. So another way of saying what we're saying here is that R1 is equal to the conjugate of R2, where when we talk about the conjugation of a complex number, we just mean to put a negative in front of the imaginary part. So the case that we're going to dispense with first is the complex case, which is important from a theory standpoint and for a completion of the different ways that this equation can go standpoint, but not usually used when you're computing with these things in practice, because most of the systems that we study using differential equations are real valued systems. So let's assume that we're starting with an indicial equation that gives rise to a pair of complex conjugate roots. So that is to say, R1 and R2 are solutions, and they're complex, and R1 is the conjugation of R2. In that case, we can still start by writing down a Frobenius series. In fact, in all of these problems, we can always start with a Frobenius series. We can assume the solution has the form y1 of x is equal to x to the r1 times the sum from n equals 0 to infinity of a n x to the n. But now, this number is complex, and so are the a n. So the power of complex numbers in mathematics is that they essentially act the same as the real numbers. But we think of the complex numbers as being two-dimensional. And the reason we think of them that way is because complex numbers have a real part and an imaginary part that live inside. And the real part and the imaginary part are both real numbers. So we think about the complex numbers as being two-dimensional if we think about them as related to the real numbers. The way that we find a solution to this differential equation is the same way that we find real and imaginary parts of a complex number. If I had a complex number a plus ib, then the real part of that number is a, and the imaginary part is b. So you can think of them as the coordinates. It's the coordinate of the part that tells you how far to go in the real direction, and the coordinate of the part that tells you how far to go in the imaginary direction. And the same exact idea of computing the real and imaginary part of a complex number actually is used to build two real valued solutions to the differential equation that are linearly independent. It's going to turn out to be the case that this thing right here contains both of the real solutions inside of it. So this contains the real solutions. How do you do that? Well, if R1 is complex and you write down y1 of x is equal to x to the r1 times the sum from n equals 0 to infinity of a n x to the n, where the a n's are complex, then you have two different solutions to the original differential equation that are given by s1 of x is the real part of y1 of x, and s2 of x is the imaginary part of y1 of x. So s1 and s2 are real linearly independent solutions. So again, more important from the standpoint of theory than the standpoint of computing in physical applications, but the fact that there is not a case that you need to avoid and the same Frobenius methods work is important to note when you're describing the entirety of a method of solution. So now I'm going to show you what the theorem looks like for the real valued cases. And remember, with real values, there's just three things that could happen. So if R1 and R2 are real solutions, to r times r minus 1 plus p naught r plus q naught is equal to 0, then we have three things that could happen. Remember that r1 and r2 could be distinct, and r1 is not equal to r2 plus a positive integer n. It could be the case that R1 equals R2. So that's called coincident. Or it could be the case that R1 and R2 are distinct and R1 is equal to R2 plus some integer n. We already know the answer to this one. So in case 1, what we showed in 11.4 was that if R1 and R2 are distinct and R1 is not equal to R2 plus n, then the form of the solutions is y1 of x is x to the R1 times the sum from n equals 0 to infinity of an x to the n. And y2 of x has exactly the same form, but with different coefficients. And I'll remind you here that the way we did this was we developed a recursion, and then we plugged the r value into the recursion to get two different recursions. So we didn't start by plugging in r to the equation. We started with a general recursion formula and then plugged the r values in, which makes the algebra much easier to do because you're not replicating work. Second case, R1 and R2 coincide. In this case, we're going to run into the problem that we ran into when we did linear differential equations with constant coefficients and we had repeated roots in the characteristic equation, which is I can't write down the same solution twice and get a linearly independent set. So it's still the case that y1 of x is equal to x to the r times the sum from n equals 0 to infinity of an x to the n. I can still find my first Frobenius series from the recursion relation. So where does the second one come in? Well, I can't just put R2 in because I get the same series back again. So what we did in the case of constant coefficient equations was we used the method of reduction of order to figure out what the form of the other solution had to be. So reduction of order was the assumption that if you knew y1, that you could find y2 by assuming that y2 of x is not a constant times y1, but a function times y1. And then you do a bunch of algebra and grinding. This is typical when you're doing reduction of order. So this technique is reduction of order. I am not asking you to grind anything out with reduction of order. I'm asking you to remember that reduction of order is a technique that exists, and this is the exact scenario that it exists for. You have a differential equation, you can get one of the solutions. How do you get another one? This is a method for constructing a second solution out of what you know about the first one. If you do that in this case, and you walk through the details, what you'll find is that the second solution has the form y1 of x times the natural log of x plus another Frobenius series. And you can still get the form of the second series by plugging all of this stuff into the differential equation. But you should at least be able to tell me what the form of the solution is. And we'll do some examples in this video of finding the form of the solutions. And in the notes, we'll do some examples of, if you know this is the form of the solution, how do you figure out an expression for the coefficients over here in this second Frobenius series? In the third case, now we're dealing with the most complicated one, which is that the solutions to the initial equation are real and they're distinct, but they differ by an integer. And here we're going to need some machinery to talk about what's happening. So the assumption we're going to make is that R1 is equal to R2 plus n, where n is a positive integer. The first thing I want to do is I want to define an equation called f. So capital FR is going to be equal to r times r minus 1 plus p naught r plus q naught. So it's a function. You put in an r, this is the value that comes out. And so solving the initial equation is actually finding the zeros of the function f of r. So if you want to solve for the indices, you can just solve fr is equal to 0. Part of the justification for defining this function is that it actually tells you what the recursion is for any equation that has a regular singular point at 0. So if you're in the situation where you're starting with the general differential equation for a regular singular point at 0, the recursion always has this form. F of r plus n, a n, is equal to the sum from k equals 0 to n minus 1 of p n minus k, k plus r, plus q n minus k, ak. So this looks like kind of a bear to work with because there's this internal sum, right? I have this sum living right here. And that sum is a sum from k equals 0 to n minus 1. So that means that whatever's going on here, if I'm on the nth step, it looks like this has n minus 1 sums to do in terms of the power series for p and q. So if p and q were e to the x or cosine of x or something, this could be really complicated. But it's still recursive. What we're saying is that the nth term is built out of all of the terms that came prior. And the things that contribute to that are the coefficients of the power series for the functions p of x and q of x. In practice, the problems that we're working with here, this sum turns out to be very simple. And the reason that it's simple is because usually we're dealing with polynomials. So nothing will be over here except for, say, p0 and p1, or q0 and q1, because we're never working with anything more complicated than an x or an x squared or a constant. So what happens if I have this sort of recursion and then the roots differ by an integer? All right, so what can go wrong here? I know that r1 is equal to r2 plus n. And I also know that because r1 is a solution to the initial equation, that it must be the case that f of r1 is 0. That's what it means to be r1 or r2. That's where they come from. So if we wrote down the formula for the recursion in terms of this function f that we've defined, f of r plus n is equal to this nasty sum So what happens at little n is equal to capital N? Remember that f of r1 is equal to 0. The first thing is we're evaluating this recursion on r2. Remember, the way we get the recursions is we write down this formula and then we plug r2 into it. And that gives us the specific recursion if r2 was equal to 1/2 or 1 or 3 or 2 or 0. Yeah, I said 2 twice. But if you put r2 in, it gives you a specific recursion that you can use to figure out the values of the coefficients ak. So if you're just tooling along, you've plugged in r2, and you're happily adding n to it. And over here, you've got the sum k equals 0 to n minus 1 of pnk times k plus n plus qn minus k times ak, and you're plodding along and going and going and going, and then all of a sudden you hit n is equal to capital N. What does this turn into? Well, the left-hand side all of a sudden turns into f of r2 plus r1 minus r2, which is f of r1, which is 0. So when you hit n equals n, the left-hand side of this recursion turns into nothing. You get 0 times an. And on the right-hand side, you have this pile of things that you're adding up, right? So everything right here, this infinite sum, is a bunch of constants that you're adding up. And they're all in terms of a0. So you pile all of this stuff together, and what you're going to end up with is an expression that looks like alpha times a0. And if you look at that for a second, you realize that essentially you've written down something that is either always true or inconsistent, because a0 is not 0. And that means if this thing is not equal to 0, and the alpha is not equal to 0, then you have 0 equal to something that's not 0, which is an inconsistent equation. Or the alpha is 0, in which case you've got an equation that says 0 equals 0, and then a capital N could be anything. It's arbitrary. Of course, that would allow you to continue solving the problem because you could keep plugging more numbers into the recursion. So that's the upshot, is that the fact that R1 and R2 are related by an integer forces the left-hand side of the recursion at some point for the second solution to collapse. And if it collapses, it could either collapse so that there's some term in the middle that you can assign any value you want to, or the entire thing is inconsistent and you need to use a different method. So the two possible cases here are, you look at f of R2 plus capital N, A capital N, is equal to the sum from n equals 0 to capital N minus 1 of P capital N minus K, K plus capital N plus Q capital N minus K, AK. And you compute that, and what you're going to end up with is 0 times AN is equal to alpha times A naught. So the number alpha is going to determine what happens. If alpha is equal to 0, then you can just keep grinding the recursion, and you end up with a second solution, y2 of x is equal to the sum from n equals 0 to infinity of bn x to the n, x to the r2. Totally fine. Standard second Frobenius series solution. But if the alpha does not disappear, which is going to be most cases, it's kind of hard to have a pile of things that just magically happen to add up to 0, then what will happen is the second solution will fail. You can't use a Frobenius series because the recursion fails, because this equation will be inconsistent. In which case, if alpha is not 0, then your second solution comes from reduction of order. It's going to, again, be y1 of x, natural log of x, plus the sum from n equals 0 to infinity of bn x to the n. So whatever happens with alpha tells you the form of the solution in this case. This is the most complicated case because it could go either way. So what's the upshot? Case 3. R1 is equal to R2 plus n for some positive integer n. Then y1 of x is equal to capital A times y1 of x natural log of x plus the sum from n equals 0 to infinity of bn x to the n, x to the r2. So you still get this Frobenius series here. And what the A does, this contains the information about what happens with the alpha. You can figure out if this part of the solution is here or not by plugging capital N into the recursion and seeing if you get a consistent equation or an inconsistent one. So A is determined by plugging in capital N to f of R2 plus n an is equal to minus the sum pn minus k, k plus n plus qn minus k, ak. Plug capital N into the recursion, check to see if the equation is consistent or not, and then that determines the form of the solution. Sorry, this should be y2 of x right here. Your second solution. The first solution is Frobenius. The second solution looks like this. All right, so those are the cases. 3 cases to worry about. So now that we've seen the 3 cases, we can look at an example of finding the form of a solution, which is really what I'm interested in here. When you're dealing with differential equations, a lot of times the most important thing is finding the form of the solution rather than the exact solution. Exact solutions are awesome when they exist, but we don't always have access to them. So working with the form of a solution is going to give us information about how the system behaves, even if we can't compute the exact coefficients. And computers can be used to compute the exact coefficients. And to do so, I recommend you check out my MATLAB demo on calculating Frobenius series. All right, so let's check out a specific example of solution finding using the theorem that we just wrote down with the 3 cases. This exact equation that we'll work with will be x squared y prime prime minus 3 plus x y prime plus 4 minus xy is equal to 0. And we're not being asked to find the solutions. We're being asked to find the general form of the solutions. So we want to find the form of y1 and y2. It's already in standard form, so I know, well, it would be in standard form after I put the x there that was supposed to be there. So I know that I've got a regular singular point at 0. So in order to solve this, I just need to figure out what p and q are. P of x is equal to minus 3 plus x. Well, that's analytic. That's great. Of course, I already knew that. And q of x is equal to 4 minus x. And I need p naught and q naught so I can find r1 and r2. P of 0 is equal to negative 3. And q of 0 is equal to 4. Plugging those numbers into the indicial equation gets r times r minus 1 minus 3r plus 4 is equal to 0, which reduces algebraically to r squared minus 4r plus 4 is 0, and so that factors pretty obviously as r minus 2 squared. So you get r is equal to 2 repeated. So we're in the case where we have one solution to the indicial equation that repeats itself. And that means that we have to go find that case of the theorem to find the form of the solutions. So let's go look and see. Well, they're not distinct, so I can't use 1. There it is. Number 2. I know the form of the solutions is a Frobenius series, and then a second series that arose from reduction of order that has the form y1x natural log of x plus another Frobenius series. So when you're asked for the general form of a solution, what you're being asked to do is to tell me what the solutions to this equation look like without actually computing the recursion. So you know, on the basis of that work, that it must be the case that that equation has solutions of the form y1 of x is equal to the sum of x to the r times an x to the n. And the second solution is the reduction of order modification of that, which is the first solution times the natural log of x plus a second Frobenius series. And that's it. That's the general form. You don't have to go any further than that. Let's look at another one. So in this problem, we're going to be dealing with the equation x squared y prime prime plus x times 1 plus 2x y prime minus 1/4 1 minus 2x y is equal to 0. Same game as before. I have to write down the indicial equation, which means I need p0 and q0. And to get those, it would be helpful if I had p and q. So p of x is 1 plus 2x. Q of x is minus 1/4 times 1 minus 2x. P of 0 is equal to 1. Q of 0 is equal to minus 1/4. When you write those into the indicial equation, what you're going to get, r times r minus 1 plus r minus 1/4 is 0. That's going to collapse into the equation r squared minus 1/4 is 0. So r is equal to plus or minus 1/2, which differ by n equals 1. From the theorem, we have two roots that are distinct but differ by an integer, and the problem is going to be this n equals 1. So what's the form of the solutions when we get started? Well, I know from the theorem that the form of the solution should be y1 of x is equal to the sum from n equals 0 to infinity. There's an x to the r1. I could be more specific than that. I could write x to the 1/2 an x to the n. And the second solution looks like capital A times y1 of x, natural log of x, plus a Frobenius series, x to the minus 1/2, n equals 0 to infinity, bn x to the n. Now, I still need to figure out if the a is 0 or 1 based on the recursion. Remember that the formula for the recursion, well, So I'm just going to figure out what the recursion is. I could plug it into that generic formula and try to figure out what the recursion is from the formula, or I could do the same thing I usually do where I put things into the series and then reduce the series by squeezing them together and get the recursion to pop out the other side. However I do it, I need to check the recursion. So when you do that, what you're going to get in this case is that the recursion has the form 4 times r plus n squared minus 1 over 4 an is equal to minus 2 times r plus n minus 1 plus 2 an minus 1. And when you take that recursion and you put in r equals minus 1/2, because remember, that's what we're trying to check to see if we can use to find a second Frobenius solution, we put that in, and all of that turns into the recursion n times n minus 1 an is equal to minus 2n minus 1 an minus 1. So this is the recurrence relation that goes with r is equal to minus 1/2. And it will either work or it's not going to work. So what does theory say we're supposed to do? It says we're supposed to take this and plug in capital N is equal to 1, because if it's going to go wrong, that's where it's going to go wrong. So what do we get when we see that? Well, as expected, the left-hand side turns into 0 times an. 0 times an. And on the right-hand side, when I plug in 1, I get minus 1 an minus 1. So 0 is equal to something that's explicitly not 0. This is inconsistent. And that means that the a in the original problem has to not be 0. It means that the second solution has got to be more complicated than just a Frobenius series. I have to use reduction of order. Of course, what I mean by that is not that I'm going to use reduction of order, but I'm going to use the solution that came from applying reduction of order. So I know that y2 of x must be of the form y1 of x natural log of x plus the sum from n equals 0 to infinity of bn x to the n with an x to the minus 1/2 out front. So because I found an inconsistent equation in the recurrence relation when I plugged in the gap between r1 and r2, that means that the second solution has got to have this term involved. If it was the case that we'd gotten something consistent here, then we wouldn't have needed this because we could just use the recurrence relation and we would have had a second series that was a Frobenius series. So that's what I expect you to be able to do when you're looking at more complicated Frobenius problems, is to predict the form of the second solution based on the values of the initial equation. And that includes determining if the recurrence relation for this type breaks down or successfully works. As I said before, if you're interested in the technical explanation of where this stuff came from, you can go and look at the accompanying videos, which kind of walk through why we believe this theorem to be true. Now, it doesn't do the gross details of grinding out a reduction of order, but if you're interested in that, all of the details of this theorem are contained in an appendix in the Good and Annan text. And it's instructive to look through it. It's not difficult mathematics, it's just long-winded. It takes a lot of space to do because you have all of these series interacting with each other and a lot of multiplication, a lot of algebra. It's instructive, but it's not very interesting to watch somebody do. So I encourage you to continue looking at this at the level of detail you're interested in. And if you're really interested, you might look at the MATLAB code that I use to produce the Frobenius series and modify it to work on some of these things. It's an interesting approach to determining explicit solutions when you can. All right, see you.